Give it another minute or so before we get started here. People are usually joining a couple minutes late. Okay, we can go ahead and get started if that's okay with you, Srinath.
Go for it.
We'll have a few more people join, I'm sure. So welcome everyone to our last seminar of the semester, believe it or not. I know it's been a little bit different, but personally I've enjoyed hearing more about what our colleagues in the department have been up to. So as most or probably all of you know, Dr. Srinath Ekkad is the department head and R.J. Reynolds professor in the MAE department. He received his PhD from Texas A&M and over the last 25 years has published hundreds of journal and conference articles in the area of heat transfer. He currently serves as the editor-in-chief for the ASME Journal of Thermal Science and Engineering Applications. So believe it or not, he's been with us for over 3 years now. It doesn't seem like that long, but previously at Virginia Tech, where he was the Associate Vice President for Research Programs and the Rolls-Royce Commonwealth Professor for Aerospace Propulsion Systems. Today he's going to be talking about heat transfer studies for gas turbine hot gas path components.
Thank you. That's good. I know, it feels like yesterday, right?
Right, 3 years already.
Yeah, a little more than 3 years now.
A little more. Mm-hmm.
So, all right, thank you. And obviously, I've never when I came here for the interview, I did not present a technical talk. It was because the way the schedule was set up, it was just a vision talk. So I thought people don't know what I do actually in my lab. I do have a pretty vibrant research program for many, many years. And I wanted to share what we are doing currently and also in the past. So a little bit of perspective on both sides. So currently there are 4 areas of research in my lab. One of them is gas turbine internal cooling, which is the impact of additive manufacturing that we are exploring. I'm going to present a lot of that today. And we also do work on the area of combustor heat transfer, which I've been working on for about 14 years in a row with the company, Solar Turbines. And this was started as a very simple experiment and now into a very complex experiment, and that rig is also moved from Virginia Tech, and we are continuing to work on that. I also work in the area of thermal management of electronics. I had a strong association with the Power Electronics Center at Virginia Tech, and we have explored some options here with our Power Electronics group, but we are continuing to do some new innovative cooling designs for power electronic modules. We also work on the external side of gas turbine heat transfer, which is the blades and looking at transonic, supersonic flows and those kind of conditions with heat transfer, but I'm not presenting that today. These are the only two areas I'm going to talk about is the internal cooling, additive manufacturing effects, and the combustor heat transfer. So let me talk with internal cooling. There's a lot of background to this, so I'm going to spend some time. I'll give you a brief overview of cooling concepts and gas turbines. I'll talk about my current research thrust, a little bit about the experimental methods we use, and also a couple of examples of novel design that we are exploring, and also what the future holds for us in terms of additive manufacturing. So if you look at it, in one aspect of gas turbines is propulsion. Other aspect of gas turbines is industrial gas turbines. Industrial gas turbines are a little bit more rigorous. So natural gas actually has changed industrial gas turbines into a powerhouse. And if you still look at it, natural gas reduces a lot of the carbon emissions. And we are still not at that position where nuclear of course is not considered an option anymore. Wind and solar are still picking up. But in the meantime, to reduce emissions, we are going from coal to natural gas. So gas turbines for power generation have become very important. aspect of our power generation systems. If you look at global power plants, we are starting to see significant reduction in CO2 and also significant improvements in efficiency, upwards of 55 to 60% for a combined cycle where we use steam and gas turbines together to improve efficiencies upwards of 60%. And if you look at the kind of series of engine turbines that have been going up, you can look at the G series and the H series, which are the new gas turbines that Department of Energy is pushing for. They are up close to 60% on the H series. The G series is already currently under in plants, and they are about 57, 58%. So what helps gas turbines? Higher improvements in aerodynamics of components to increase loading. That means we can get more power out of every blade and every component in there. We can improve cooling to ensure life. That means we don't have to stop the turbine to repair. And the last one is improved materials, which will also help you survive the environment that we are putting this airfoils in. If you look at the propulsion engine is a little bit more simpler. It's basically you compress, combust, and expand. When you expand through the turbine, you get the power to run the compressor. We inject the fuel into the combustor to generate the power. And the exhaust, which goes through a nozzle, provides you the high jet that you get to thrust your aircraft forward. But you look inside the red part, which is, I'm only focusing on the combustor and this turbine area. These are the two areas which are the hottest in the turbine. And I'll give you some numbers on that in a minute. But basically, this area, the materials are already facing temperatures which are significantly higher than what the materials can handle. So you need naturally some kind of cooling. And if you look at the cooling schemes later on, as I show you, the cooling is not really done by any particular water, or you're injecting water or anything like that. You are basically you are compressing 100% of the air, but you're taking about 10% of the air and bypassing the combustor and using the 10% air to cool the turbines so that you get back the air back into the gas path before it goes out to the exhaust system. The reason we do that is in aircraft engines, you can't carry cooling systems, extra systems, because heavier adds weight to the plane, adds weight to the engine. So we had always tended to use the cooling air from there. But when I say cooling air, it's not really cold air. The air in the gas turbine main part is upwards of 1300, 1400 centigrade, but the cooling air is about 600 to 800 degrees centigrade. So it's not really cold air, it is cooler air, and essentially the part can survive that environment. If you look at how the cooling air comes in, it comes from underneath the combustor, and all the red paths are the arrows are showing where the coolant comes in and enters all the blades and in the turbine section, and then passes inside the blades and then comes out and joins the main flow and exhausts at the back of the engine. If you look at the technology, how it's developed in the 1960s, the temperatures were very, very low, so you could use stainless steel components. So it was relatively mild, the temperature, so the parts could survive. So there was not much cooling except for some little hole to let some air pass through, and also reduce some of the weight of the blade to make it hollow. Then as you go to 70s, we started seeing the temperatures go upwards of 1200, 1100, 1200 C. Immediately cooling became an essential, so they started putting holes on the blades to let some of the cooler air come out and protect and create a boundary layer cooling effect. And as we went to higher temperatures, the insides of the blade became a lot more complex with multi-passes of flows so that you can extract heat out of the blade and push it out with the cooling air and without losing the part itself. And if you just look at the simple example, the compressor combustor turbine, right? If you look at how it's been, you can see that turbine temperature is now at upwards of 2200 Kelvin. That is almost 2000 C. These are primarily in military engines. Commercial engines are typically around 1800 C, 1700, 1800 C, and industrial gas turbines are around 1500, 1600 C. So it depends on the application, and as we went up in temperature, the cooling configuration became more and more complicated. And as you can see, now the surface of the blade is a lot more complicated too. If this, you look at it, this is the metal, which is the titanium or a nickel-based alloy. And then you have a bond coat, and then you add the zirconium, yttrium stabilized zirconium layer, which is basically what is called a thermal barrier coating. And then, of course, you have the cooling air. So you have a lot more things going on the surface of the blade, thanks to material scientists, because they have invented very high temperature coatings that can protect the metal so that the metal doesn't burn off. And when the burn off does occur, it affects only the coating. So when you take the part out, you actually basically coat the part again and then reuse the part without losing the part. So typical turbine blade, even bulk, costs about $5,000. So if you are looking at 48 blades in the first stage of your turbine, then you're looking at upwards of $250,000 to replace all the blades, and every blade counts. So and it's also expensive to remake them. So it's very important that we come up with ways to protect the blades without losing the blade itself. So the coating actually is one of the best inventions in the past 20 years that has helped with cooling. And it also allows us to go to higher temperatures. So as you can see, with TBCs and film cooling, we are already hitting about 1500 to 1700 degrees C. And there are a lot more history behind it. And then also in terms of materials, what kind of materials we are using, we are now starting to look at silicon nitride based CMCs. We are also looking at eutectic oxide based CMCs. They're all trying to push. So in 2035, we hope that 1700, 1750C will be fairly easy to do in a gas turbine and keep the parts going. So currently we are around here in the second generation SX. We are at the TBC level. Anything above beyond that is all experimental. It's already been tried. It's not like they don't know how to do it. They already know how to do it, but it's just that you have to get everything certified by FAA to ensure that these parts will comply. So if you look at the turbine, it's the blade itself. The flow comes in, goes across a typical airfoil-like design, but with much more stronger angles. You're looking at the turning angles upwards of 100 degrees. So the flow comes in, turns almost 100 degrees when it turns. And there is the pressure side, which is this side, and then the suction side, which is the lower pressure side. So basically you get lift, and which forces the blade to turn. And because of that, because of this geometry, the airfoil surface curvature, there's the boundary layer transitional behavior that occurs where the flow hits the leading edge, and then two boundary layers start, one on the pressure side, one on the suction side. On the suction side, the boundary layer goes to turbulent, boundary layer from laminar instantaneously, whereas on the pressure side, it sustains the laminar boundary layer a little longer and then eventually becomes a transitional boundary layer to a turbulent boundary layer. In addition to that, the air coming out of the combustor, which hits the blade, is also heavily turbulent. You're looking at upwards of 15 to 20% free stream turbulence. And then because you coat the surface with TBC, it tends to make it slightly rougher. And when it's rough, heat transfer enhances. Then of course you have these holes in the middle, which tend to trip your boundary layer. That means you got higher heat transfer coefficient right behind the holes. Then you got flow separation and reattachment, which could occur at non-optimized design conditions. And of course, the exit Mach numbers, the Mach numbers hitting the blade are typically around 0.4, 0.5 Mach number. And the exit of the blade is about, it could be about 0.8, 0.7. Somewhere in the middle of the blade, it's about 1.1 Mach number. And then you have the Reynolds number effect, which is basically dictates the heat transfer aspect of it. So if you take into this, the turbine inlet temperature is about 1700 degrees C. The blade material melting point currently is 1000 degrees C. I mean, if you add the TBC coating, then you can go up to 1200 C. And you have cooling temperature from the compressor that's coming in at 700 C. So basically, I have to use the 700 C to make sure that the metal temperature comes down to 1000 degrees C while it is exposed to conditions which has 1700 C. To make this efficient, and of course, remember, I also told you at the beginning, I have only 10% of the air that I get from the compressor. That means I have limited amount of air at a particular pressure that needs to be used to cool the blade, right? So now the point is, I have a limited amount of cooling air. I have to get this temperature below 1000 degrees centigrade so that it can sustain life. At the same time, I have to be very, very effective in where I put the cooling. So not only do I need to know where to put the cooling, I need to know how much cooling at every location, and also to know how effective the cooling is. So all this stuff is the most critical part of our work. So if you look at the blade itself design, if you look at a blade design, the mechanical designer wants something that's tapered, primarily because the stresses when you're rotating something go higher as you go up. So if you make it thinner, the potential of surviving mechanical stresses is higher, so you tend to make it thinner. If you go to an aerodynamics person, in terms of wake effects, in terms of all the boundary layer effects, you would like something very thin, razor sharp. And of course, if I want me to cool it, as a thermal designer, I want something where I can put cooling air. That means like a balloon or a tube. Essentially, all these three people have come together with a shape which is more common. So you have a little bit more space in the middle front part of the blade, maintaining the shape the aerodynamic wants, and the flow, actually the blade tapers from bottom to top. So it's a 3D cooled air structure. Then I add all these holes as a thermal designer to let cooling air come through, and inside the blade, there are a lot of passages that are doing. Outside the hole itself, there are different kinds of effects. You have surface effects, you have trailing edge film that's coming out of the back of the blade. You have fillets, which help you connect the blade to the base. You have interfaces. That means where there is a gap here, where the rotating component and the non-rotating component are mismatched. So there has to be a gap there. There will be a seal there, but the seal is not perfect. Then you have 3D aero effects, and then of course you have all kinds of holes coming out everywhere, and all these contribute to heat transfer problems. So I think I repeated that. So if you look at turbine cooling technologies, you have high pressure turbine airfoils, which is the first two stages of the airfoil of the turbine, which are the most exposed to the hottest conditions. You can actually pre-treat your cooling fluid, that is the air that I was talking about. Compressor can actually put an intercooler in there and reduce the cooling, but again, it adds bulk. So we are trying these kind of things in industrial gas turbines because they're not flying, but in aircraft engines, it's not going to be possible. Then you have the internal convective cooling, which is basically guiding the cooling through the holes to the channels inside the blade and making sure that it enhances the heat transfer. Then you got the film cooling, which is coming out of the holes. That's going to provide the cooling coating along the surface. And then you have the materials selection, which is choosing the right amount of material so it can sustain it. In addition to all this, you have to combine all this together and call the thermal mechanical design to come up with acceptable levels of thermal stress and aeromechanical response, which will ensure that the blade will survive. Just give you an idea, a military engine blade, expected life of survival is 300 to 500 hours. Commercial engine, aircraft engine blade is around 3,500 to 5,000 hours. And if you're looking at an industrial gas turbine blade, you're looking at upwards of 30,000 hours. So that means the same part has to survive these conditions. Because the temperature goes down, the durability needs go down, and essentially you can increase the time of replacement. So as a heat transfer person, I look at it as a simple 1D analysis here. I got a gas hitting my outer wall, and there's a heat transfer coefficient associated with that. And I have that as a resistance, as a convective resistance. Then I have the resistance. Actually, I'm not even including the resistance. Of course, there's the radiative resistance also, which is also added here. And the TBC coating itself, the interface resistance, which I have not added. Then you have the thermal conductivity of the TBC and the thickness of the TBC that dictates the heat transfer into the blade. And then you got the interface between the TBC and metal where the bond coating there. And then you actually have to consider the bond coating, even though it's very small, it just contributes some resistance. Then you have the metal, and then you got the metal temperature, and then you have the cooling heat transfer coefficient inside. So you want to reduce the heat transfer here and increase the heat transfer here. So I'm going to focus on this side today. I'm not focusing on this side. So the heat transfer coefficient has to be enhanced. But remember, I again told you that amount of coolant is limited, amount of pressure drop is limited. So I have to ensure that my heat transfer coefficient is higher. So if you take this baseline, NU0 is basically a channel which doesn't have any features on it, just a straight channel. You can get a heat transfer estimate fairly quickly. But how much am I enhancing that heat transfer by adding features inside the blade, like this turns and holes and all the stuff that I'm adding in the surface is going to enhance my heat transfer to even 3.54 times what a smooth channel will be, with the idea that it will not increase my pumping power. So what we do in our world is we take the heat transfer coefficient enhancement and the increase in pressure drop, and when you do, it's a Reynolds number matching here. And if you look at it, you take the heat transfer coefficient enhancement divided by the pressure drop enhancement to the power of 1/3. If this eta value is greater than 1, then your design is technically better than the previous design. So you can compare multiple designs like that. So you can have design 1 versus design 2 and look at how the design 1 versus design 2 is. So idea is to enhance this thermal head. So I'm giving you a brief, this is how the blade looks like. There are multiple options here. The blades have multiple channels, and then you have the spin fins at the back of the blade that helps you enhance heat transfer and also provides you structural advantages. And this is a rotating blade. Then if you look at a vane, you see a lot of different kinds of cooling schemes for vanes. Vanes tend to use what is called impingement cooling, because impingement cooling is easier to work in a non-rotating condition, and you can actually create the sleeves for 3D, not for 3D, but for traditional manufacturing. You can actually make non-rotating parts because you can add the sleeves to enhance the heat transfer through impingement cooling. So where are we today? This is all the cooling designs that we have currently. We have impingement cooling is right here, even though we don't use it in turbine blades, we use it in turbine vanes. Turbulated channels are here. Rotating impingement is pretty good. Again, we don't use it. We have pin fins, swirl wall jets, ribs that are high performance ribs. And if you look at the rotational effect, I'll talk about this later. If you have a rotational benefit, you get a higher heat transfer. If you have a rotational deficit, you get a low heat transfer. But this is the Reynolds analogy, which compares the pressure drop to heat transfer. And what we want to do is move our research thrust so that we get into this area where we get very high heat transfer coefficients, but relatively low pressure drop. So we have started looking at impingement cooling, novel rib turbulators, swirl-based impingement, channels which have mesh, and then we can put twisted tapes in there, high efficiency pin fins, which also shows the CFD there, and also some swirling flows that we can introduce through other ways. So the idea is to go to research thrust to move that distance, move that direction so that you can get higher heat transfer with lower pressure drop. Just to give you an idea, I've been doing this for about 30 years now, starting from my master's. This is some of my PhD work that I'm showing on the right side. And this is some of the examples of other work that my previous group at Texas A&M has been working on. So we took all the data that's available in the literature, and we put it on a plot where we looked at the heat transfer enhancement versus the pressure drop enhancement. And if you look at, these are what is called the dimples, which are basically concavities in the surface. And this is all the rib data that's out there, different kinds of ribs, different kinds of geometries, and all the stuff. So we think that we want to push our design to go this way, somewhere here, where we get heat transfer enhancement upwards of 4 to 5, and the pressure drop increases about 6 to 8. So that's where the goal is. But the industry, most of the people who are doing research are going this direction, trying to enhance heat transfer without taking into account the pressure drop. So I will talk about some of that work that I've done previously so that then you get an idea about what we do. So we do a lot of transient liquid crystal thermography using 1D semi-infinite conduction assumption, narrowband liquid crystals. So we get data, detailed 2D data of heat transfer on the surfaces. This is for impingement on metal surfaces using heater foils. Again, we do CFD to just understand the flow. Again, we can show you some metal-based cooling schemes with heated flows and heated surfaces so that we can actually measure average heat transfer instead of local heat transfer like that. The local heat transfer cannot be done on metal surfaces because this model that I've created here cannot work on metal. It can only work on plastic surfaces. So I'll tell you a little bit more about why that is. One example of a very complex scheme we did some many years back was to create an impingement channel like this, where the flow would come in and impinge here and then go into the side channels. It was patented. As you can see, US patent, we have a couple of patents. We also have a patent. And we found out that our heat transfer compared to a traditional impingement was significantly enhanced, especially downstream. So you can see the colors. As the color gets redder, the heat transfer is better. So that's one of the work we did in 2006, 2007. This is the work we did, one of my PhD students, Pritish, he did looking at oblique impingement to enhance heat transfer because it creates swirl, and swirl is basically enhanced turbulence. Enhanced turbulence will enhance heat transfer. So that was one of the work. This is the work we did for Rolls-Royce. They came to us with the actual blade design. This is how the blade looks like. And then we simplified the blade to look like this because it's easier to make it. At the time, I didn't have additive manufacturing. This was about a 2012 timeframe. So we made everything in plastic, put together the parts, and measured heat transfer on every surface of the blade. And what you're going to see is how non-uniform the heat transfer coefficients are on the surface. On this channel, you see that very low heat transfer on this surface, but on this surface, you see a very significantly high heat transfer. What you're seeing is this distance could be like about 30 millimeter, and you are seeing a significant difference in heat transfer. Similarly, you can see this side and this side showing differential heat transfer. Again, this side is showing different. And then last channel, again, you see there's absolutely no cooling at the tip of the blade as the flow goes up. So what we did is we presented this data, and that led to some more work from GE. And this was looking at dimples and concavities in flows, and also ribs, and comparing all this. If you have straight ribs, angle ribs, V ribs, then you have concavities which are put far apart, concavities that are put together, concavities are put even closer to see how the heat transfer enhances. One thing you'll clearly see is the ribs tend to enhance heat transfer significantly, a lot more than concavities. But the only problem is this also enhances pressure drop significantly more than this. So where is the solution in this? We also looked at different kinds of pins. Here I'm showing you circular pin fins, hexagonal pin fins, triangular pin fins, diamond pin fins. As you can see, diamonds seem to be better. Again, we cannot make diamond pin fins with the current manufacturing techniques. That's something that we have to think about. This was work done by Jaideep and his PhD as part of his PhD. Again, so where are we today? So heat transfer enhancement research, major questions, right? We have several existing concepts, but the heat transfer enhancement levels are 3. And if we want to go higher with our traditional knowledge, we are going to see an increased pressure drop. That means the heat transfer overall is going to decrease because we cannot push amount of flow that we need. And the designs that we are talking about are not very efficient because they tend to not increase the heat transfer significantly to give you a pressure drop value there. So effective designs were challenged by manufacturability. But in the last 4 or 5 years, we are starting to see additive manufacturing come out in a big way. And we are in my lab, the idea is to look at the possibility to break this barrier that's set up here from traditional manufacturing to create higher heat transfer enhancement levels without compromising on the pressure drop. So one of the concepts we are looking at is, can we do 2 different cooling concepts and put it together to get this higher heat transfer without enhancing heat transfer? I showed you concavities and ribs. Can you put them together? And what happens to the pressure drop when the 2 concepts are added? Is it remaining at the highest level of the bigger, the worser design, or the combination actually helps you reduce it further? There are endless combinations that must have a higher thermal hydraulic performance, but have never been investigated. That means the market never demanded, because when I was at Rolls-Royce for 2 years, I used to go to my boss and say, hey, we could do this. And invariably, the manufacturing guy would say, we cannot make it. We cannot do this. We cannot really do anything that you're talking about, because we cannot do it in the traditional casting mold where you cannot pull the mold out, and we cannot have features that stick out because the mold will not come off. So one of the biggest challenges of casting was that you cannot do many of these extruding surfaces that we are looking at. So my research is focused on answering these crucial questions posed by the rapidly changing technologies. In fact, our additive manufacturing lab is one of the keys in my ability to deliver some of these ideas. The gas turbine field, of course, demands innovative cooling solutions by using AM to the full capacity, but it's still going a long way away. So DMLS is the traditional method that we prefer in the gas turbine industry, which is called direct metal laser sintering. It's basically you take the powder of the material that you are going to do, and using a laser you sinter it, and then you make the part that you want in the shape that you want it. And it is additive manufacturing, so you essentially don't use any more material than needed to make the parts. So this is one of the examples that TurboCam has made, and this is another one that that another company has made here, GE, through GE. Again, microchannels have been made in many years in metal. We have also made our own microchannels in the recent times. But a lot of work is going on in this area. In fact, you will be surprised to know that Pratt & Whitney has been using 3D printed parts since 1980. Metal AM parts are already being used in Pratt & Whitney 1500G engines, which are going to be used by Bombardier. Pratt & Whitney pioneered and actually has developed a way to make powder-based nickel superalloys that can then be used in DMLS to make blades. And they also can print the 3D printing. And a large effort of the work is going on in heat transfer testing at Penn State with Karen Thoele. GE Aviation, instead of building their own technology, they went about buying all the additive manufacturing companies out there. So they have bought a bunch of additive manufacturing companies in the recent time. They already started manufacturing a lot of parts in their LEAP engine, which was going to be on the 737 MAX, has a lot of 3D printed parts. And now their 9X engines, which is the largest engine ever built, that also has a lot of 3D printed parts, but still not in the hot gas path, because they cannot afford to make hot gas path components yet, because FAA is not willing to consider it until they're absolutely sure that these parts can survive the conditions and the operating mission, like where takeoff, landing, all that stuff, and also potentially flying into ash, volcanic ash or something like that. All that tests have to be done before FAA is going to allow these parts. And I worked with Rolls-Royce. Rolls-Royce is actually behind on this, but their latest engine, XWB, has some AM manufactured parts, but they are not, again, in the hot gas path. So in terms of research, we had a big project with GE a few years back where we are looking at 3D printed micro roughness impingement heat transfer that helped us in understanding what kind of features that can be made. They would send us the components and we would test them and tell them how the parts perform. Ohio State had a big project with DOE where they were going to manufacture a DMLS-based alloy Vane, turbine Vane, but that project has been going on for 5 years, and I haven't seen anything come out of that. But other one, actually very forward, very ahead of everybody else, is the additive manufactured studies that Karen Thoele is doing at Penn State. So important takeaways from Karen Thoele: that AM is great news, but advanced cooling concepts still need to be developed. One of the things you need to realize is what the designs that we have come up with in the last 40 years are primarily based off on casting-based manufacturing. Now that you convert it and say, well, you can use AM, you don't actually have to design the same thing and print the same thing. We can actually come up with more novel designs, and those are not been actually designed yet. So that's where we are coming in. So we are going to develop novel cooling technologies that can be fabricated on engine similar length scales and tested under engine conditions. So we are going to test all that in our lab if we can make them. First of all is to test the concept and then build the actual blade. What is expected from, we can get new internal cooling designs, both for stationary airfoils and rotational airfoils. We can do concepts for numerical optimization of the designs, and also look at fabrication, potentially work with the Camel group here and make some conceptual designs. We are working with, currently exploring with Honeywell and Siemens to look at some of the designs and also do some testing in-house and I'll come up with new designs. So what does AM give us? AM is going. There's no way we are going to stop this force. So AM is going to change it. And it's being noticed by the gas turbine industry. And as you can see, the parts are getting made and a lot more now. Service and parts, as you can see, the service and parts have grown quite a bit in AM. So this is the design space. I actually have a project with a company. Unfortunately, I can't present the results on that. It's proprietary work where they send me parts that they have made with new manufacturing techniques to compare with what the GE or Pratt & Whitney or Rolls-Royce makes, and then I test it, and then they actually get FAA certification from me, and then they actually go ahead and sell those parts to the aircraft companies like Delta and American and United. So where are we on turbine cooling? These are 19 patents from the 1960s that I just pulled out. These have already been there. These are all the patents that already exist in the literature, and none of them have actually ever gone into an engine. So you can see that 1960s people have already thought about complicated designs like this. We couldn't make them, we couldn't test them, so we left them. We let them go, but they are there. And recently, this is a couple of designs that came out at the 2016 Turbo Expo, and it shows a penetrating cooling system where the air comes in and it penetrates through holes across, and also enhances heat transfer with interesting features where they got small little sleeves right near the wall where the cooling air would get close enough and take the heat away much more effectively. Then there is this mesh cooling where you can create this mesh structures. Again, you cannot do it in traditional casting, so then you can make those blades. Okay, now you can see the channels are changing in direction instead of just going straight up and down. You can see that these are different kind of features in there, and this one has a little bit of a crisscross channels that are also different. All these designs are already being explored, and they are trying to be manufactured through AM. We cannot make it with traditional manufacturing, so this will be tested in a few years. Again, some more examples of impingement cooling. Again, very, very interesting features. Again, these were in the 70s and 80s, double wall cooling concepts. These are rib turbulator concepts where the ribs are broken with holes here so that the flow will go in between and enhance further turbulence and increase heat transfer. These are some of the stuff that my advisor did in 1984 and 88. I'm telling you, other than this design and this design, none of the other designs are in, and this design, sorry, these are the only designs that are available in the engine right now. All the broken ribs, the V ribs, the W ribs, all this stuff, none of them are in an engine. So what you're seeing is some people have done this work over 30 years back with ideas like this, but the manufacturing had not caught up. Now with AM, we are able to do all this. So hopefully all these designs that are extremely efficient in heat transfer are going to be now considered as part of the next generation of gas turbine blades. So now I'll quickly run over my experimental methods. One of the things I really wanted to show you was these are the rigs. Of course, these are pictures from Virginia Tech, but I didn't get new pictures. We are still moving to MAE West, haven't done all that stuff. So this is our rotating rig. This is our benchtop experimental rigs. This is the rig that we use for metal cooling, metal-based cooling. And this kind of shows you a schematic of how the rotating rig works. In the rotating rig, what we do is we actually coat the surface. It's a plastic rig. We coat it with not plexiglass rig. We coat it with liquid crystals, which change color, thermochromic liquid crystals, which change color based on temperature. That is what I did my PhD on in those days. And then what we do is we coat and then take images of the color changes during the experiment, download the images, convert the images back to temperature, and then calculate the heat transfer coefficient. So just give you an idea how an experiment looks. This is my rotating rig. As you can see, it's coated blue because it's right now at room temperature, it's blue. As I send in cooling air, it's going to go from blue to green to red and again become colorless, okay? But what I'm showing you is I'm showing side one, the opposite side, and this is the top, which is on this side. And there are three cameras they're looking at, and this is the outside camera, which is going to look at it while it's rotating. It's rotating at 700 RPM, and these three cameras are going to take the data. So you see that these three are rotating right now. You can see the color changes occurring. So what you're seeing is basically the color changes occur. So this area where the color change occurred faster is typically the higher heat transfer coefficient. And as the flow turns around and it goes through, actually flow comes in this way and it goes through this, the lower heat transfer is on the first pass. The second pass actually is higher heat transfer. And you can see some changes in the color here. So we can convert this into heat transfer and get heat transfer data. So that's the rotation. For stationary, of course, it's easier. All we do is send it through a plexiglass rig and make the same measurements. how do we calculate the heat transfer coefficient from the images? What the images give me is the wall temperature response with respect to time. So we start the experiment when the cooler air enters the test rig, it starts changing color. So time 0, the air enters, and then we start seeing the color changes. We record the color changes, and we know the wall temperature from the color at every pixel on the test surface. And then we take each pixel as an independent pixel and apply what is called the 1D transient heat conduction equation, which is assuming that the heat transfer only occurs into the plane, into the wall, and we apply the initial condition that everything is at initial temperature, and then at the wall we have the convective heat transfer, and down way deep away from the wall, the temperature doesn't change because we are using plexiglass. There is no conduction, so you will not see, it's called a semi-infinite wall. So you basically won't see heat transfer go through the wall. It only stays at the skin of the wall. And then we convert this equation, which is the equation in a very standard undergraduate textbook, and then say put Z equal to 0 here, which is the T wall temperature. And then we put Z, this term vanishes, this term becomes 1, this term vanishes, and all we have is this beta term, which is the heat transfer coefficient in it. Alpha is the thermal diffusivity of the plexiglass, and K is the thermal conductivity of the plexiglass, and the T is the time at which the T wall appears. So you know T wall and time. The only unknown here is heat transfer coefficient. We know the properties of the material because it's plexiglass. We know the properties, and they tend to be very, very low because that's the only way you can do the experiment in a reasonable amount of time. The experiment is done in 20 seconds. So how do we convert the color to temperature? From the color, what we do is we take the color and convert it into hue of the color. Hue of the color is the amount of color, even whether it's red, green, blue, hue basically goes from 0 to 256. 0 is fully black, 256 is fully white. So red, green, blue, so red is somewhere here and blue is somewhere here. This is the hue as it goes. And early on in the liquid crystal world, in 1990, somebody found out that hue is directly linearly related to the wall temperature. So what we did was we do a calibration in the experiment where we calculate our hue from the color, and then we have a thermocouple which measures the temperature right at the same region, and then we plot the hue versus temperature, and then we get a linear relationship between hue versus temperature, and then we take all the images and convert the hue at any instant of time to temperature. Then you get a temperature field at every instant, every frame in the experiment, and then we convert that to the heat transfer coefficient. So this is how our experiment looks like, right? For constant, if our mainstream temperature was constant, that means the air temperature in the experiment remains constant, then this is the equation we use. But in our experiment, we find out that the air comes in at 20 C and goes down, and every location has a different temperature response. So we take into account all of this using Duhamel superposition integral, where we divide this into multiple time steps and break it up into hundreds of time steps, and then calculate every time steps to account for the slope of this temperature change. So if a color change occurs in 5 seconds, this is the amount of slope you would take. If it occurs at time 20 seconds, then this is all the information you would take. So that is how we calculate the heat transfer coefficient to make it more accurate, and we can get it within 6 to 8% uncertainty. So this is how a heat transfer coefficient maps looks like for liquid crystal data for an impingement cooling system. And you can see all the red spots are where the jets are hitting, and you can see the heat transfer coefficients are. And this is where we do our calibration. That's why you don't see the data here, because the calibration curve is got from that point. So I want to get into something that I'm doing right now, which is combining two different experiments using ribs and dimples. So if you use ribs and dimples, we have ribs here, we have dimples here, and dimples and ribs together. So how do you enhance it? So if you look at it, this is my ribs only, which is significantly high heat transfer as I'm getting it. Then you have dimples, and you can see very localized heat transfer enhancement because of the flow going into the cavity and coming out and reattaching and enhancing heat transfer. And when you add both of them, you can see a substantial amount of red on both channels. what it proves to you is if I take this and this together, I get a significantly higher heat transfer. So I change the rib to W to see if W helps, and if I get the same result, it doesn't matter what kind of rib I use, what kind of dimples I use, I always get higher heat transfer when I combine these two. Dimples cannot be made in the conventional manufacturing in a blade, but additive manufacturing can do that. So what happened is we were able to take dimples and ribs and move the efficient design domain closer to efficient design domain, which is getting up to 4.5 heat transfer, and pressure drop only went up a little bit. I'm sorry, the ribs should be actually here, but we got a higher heat transfer coefficient. So, and then we are also doing some impingement cooling with different kinds of 3D printed surfaces. These are micro pin fins with cubic, micro, and concentric micro fins, and you can see micro fins can enhance heat transfer quite a bit. And then the increase in heat flux, we can get up to 73% higher heat flux reduction than traditional flat surface impingement. So this is 3D printed surfaces as you were watching. This is our micro roughness. This is a circular pin fin. This is a square pin fin, and this is a concentric pin fin. And these were actually made with copper at Virginia Tech with my additive manufacturing colleague there. And we found out that we can make such detail, and we have some flaws. You can see some flaws here, but in all, we got pretty good cubic fins, but in the concentric pin fins, we didn't get it perfect, but we still got much higher heat transfer with concentric pin fins. So we can actually see that by making 3D printed surfaces, we can actually enhance heat transfer significantly more than traditional designs. So in terms of rotation, we also do a lot of rotational heat transfer where we look at the effect of rotation with respect to the flow velocity. We look at the buoyancy, which is the difference between wall temperature and cooling air. And we look at how we can rotate a channel like this, as I showed you in the experiment. The flow comes in, goes through the 180-degree channel. This is different Reynolds number. But if you rotate it, what happens is one side gets higher heat transfer, one side gets lower heat transfer. That's primarily because if you're in a room that's rotating, you tend to fall back and try to hit the wall that is non-rotating, right? So that's behind you. So that's why we call it the trailing side and the leading side. The leading side is what is in front of the rotation, and trailing side is behind the rotation and enhances heat transfer differently. But once you add ribs, that effect reduces a little bit, but still it's there. So that's what we are trying to reduce that. So you can see the difference. The leading side has a much higher heat transfer and the trailing side has a much lower heat transfer, and that causes extra thermal stress. And this is where the problem is. The thermal stress between these two surfaces, within 40 millimeter away from each other, can cause a significant damage to the part. So we are trying to make these two surfaces be equal. So we came up with a design where we took the channel which looks like this, and with the heat transfer that looks like this, to a channel that looks like this, where the flow would come in here and go out like that. Flow would come in here and go out like that. And what it does is it changes the flow structures, especially the rotational effects on Coriolis force and centrifugal buoyancy and all this stuff. So as you can see, the red are the major structures. The blue is when you add centrifugal buoyancy to it, to the surfaces, and then you can see the effect of heat transfer. So that now suddenly when you see the new channel, you see that there are 4 vortices that have been created instead of 2 vortices. And you also see that centrifugal buoyancy actually stabilizes the flow and then enhances the heat transfer more evenly. So what we did is we saw that the data looks almost identical. This is rotation, no rotation. And you can see the difference is not much. So basically we have effectively reduced the effect of rotation by changing the design of heat transfer. This was something that I wrote a proposal when I was in grad school with my advisor. Didn't get funded at that time, but luckily we have the ability to do this. We did this work with as Prashant's dissertation part of that. I'm going to quickly run into my combustor heat transfer and show you a couple of things. I have maybe 5 minutes for that. This is an interesting problem that came to me about 15 years back. Nobody was studying heat transfer inside combustors to find out how we can effectively cool combustors. So the idea was that to reduce NOx, you have to run the combustor very, very lean. That means you have to push more air and make and less fuel to improve the combustion at a lower equivalence ratio, so that you still get the temperature that you want, but you cannot use much cooling for the combustors. That means when you cannot use cooling, that means you need to know the heat transfer very effectively. In the past, the cooling design used to be like this, where about 40% of the air would come through the primary combustion zone, and the rest of the air would come in through these sleeves to help cool this surface and also reduce the temperature. So here you would have a very rich burning flame, very high temperature, upwards of 3000 Fahrenheit. And as it goes and mixes with the air around the edges and comes down, it will be around 1800 to 2000 F. So the idea was that this air would come in and help. But what happened was, in the primary region, you're producing NOx. And at the secondary region where the coal mixes, you're producing CO. So you're getting detrimental effects of both CO and NOx. So one thing was to reduce the amount of air coming out of this and also increase the amount of air coming here. So you can reduce the NOx, reduce the CO, and that's basically what the designs from Solar Turbine was, to make the combustor bigger. So you reduce the firing temperature to 2900 F from 3600 F, and reducing the cooling air that comes out of the walls. So essentially now you're sending only 50% of the air compared to 70% of the air to the cooling schemes, and that reduces some of the effects. And you can see the designs are very different. This is a conventional combustor versus a new combustor that we helped design. So I'm going to skip all this. This is a little bit on the background on how swirl flow works to improve combustion. I can share this with you all if you want, if you're interested in going through. Many people have asked this. This is how we measure heat transfer in there. We have heat flux gauges and all. This is my rig that I moved from Virginia Tech here. We built this with DOE funding. At that time, when we first started, we didn't have a combustor. We were just doing room temperature experiments with swirling flow to show combustor heat transfer. But DOE and Solar funded me about 2014 to build a combustor rig, which we can actually make measurements in both the flow and heat transfer. So the combustor actually is an optical combustor. You can actually see it. We preheat the air with a 192 kilowatt heater. The air comes in about 250 C and goes in, and the fuel and air mix here and then go through the combustor, and then you can see that. So just give you an idea, this is the combustor. That's what the combustor looks like. The fuel nozzle is actually an industrial fuel nozzle from Solar Turbines, which was retrofitted into a rig. The fuel and air mix inside here and come out, and that's where the primary combustion occurs. And right in the middle is called the pilot hole. That's where we send in the fuel first, so that we can ignite it, and then once we ignite it, we send the air and the fuel from the sides. So quickly, there's more. So I'm going to show you. This is all background again. How we do PIV? This is in high temperature. Many of you know what PIV is. We use a high-speed camera. We have a dual head 527 nanometer beam, which we use to produce laser pulses, and then we seed with alumina particles. And you can see that images here. This is how our pilot is running at 0%. Pilot is at 0%, and then the flame is primarily burning purely from the main flame. But then if I add the pilot, you can see a central burning point here. This is with the equivalence ratio of 0.65 and 50,000 Reynolds number. But you can see how blue the flame is, right? It is a pretty clean burning flame. As you know, many of you know, if you have a gas stove at home with natural gas, if you get a blue flame, it's much more cleaner than a red flame. We use different kinds of fuel. This shows you our test rig and experiments. And you can see the flame burning fully with the video camera, and the laser pulses are going right now. And then we take the images, and this is how the non-reacting versus reacting looks like. The non-reacting, you can clearly see that the flow is not fully structured. It comes out and it kind of flakes off. It never comes near the wall. Whereas when you see reacting, actually reacting makes the flow much more structured and coherent. And you actually see the pilot flame also here, and you can see the reaction here. This is the raw images of the reacting versus non-reacting flame, right? This is basically velocities. So if you look at what is happening, you can see a shear layer right here, and you can see zero velocity location. The flow goes in, hits, and then comes back. This is the pilot flame. And then this is a recirculation zone right in this corner. We are able to capture all the conditions that affect potentially affect the heat transfer in the thing. So this gives you an idea about a little bit about non-reacting versus reacting. You can see the velocities are much more significant in reacting flows because of the energization of the burning of the fuel. So we can do heat transfer measurements on the wall, where we coat the wall with the black paint and then make measurements on the outer wall and the inner wall, and then use a 2D methodology to calculate the heat flux on the wall. So we vary a lot of components, a lot of parts, and then we also look at Reynolds number variation, equivalence ratio variation. We look at pilot variation and look at the heat flux and see what affects the heat flux. We also measure the temperature of the flow. This was a interesting experiment we did many years ago, because there's no way to measure the fuel flame temperature non-intrusively. So we went ahead and did it with intrusively. As you can see, a thermocouple that's going automated and making measurements inside the flame. And these are the points that it measured. We had programmed everything. It would go in. But in between, you'll see that the flame gets bigger because the thermocouple starts acting like a flame holder. And we don't want that. So we stop that immediately and move the in and out, so that we don't want a flame holder. And then we keep moving. We got the data. And then when we got the data, this is what our measurement gave us. And this is what our CFD gave us. As you can see, the CFD cannot predict the recirculation zone very effectively, but it does predict the pilot zone as a lower temperature than the experiments. But you certainly see there is a lot of similarities between CFD and experiment. That was very nice to see, even with an intrusive method like what we did, which is not convenient. So I'm going to stop here. I want to know whether you want to write this. My former and current students were instrumental in this. Current students are still going on. Many of them are graduating. Kishore, Srivatsan, and Sanskar will be graduating this year. But in the past, many of my PhD students have been very instrumental in delivering all this work. Of course, my funding agencies that have given me money and continue to give me money to do this kind of work. So as I said, we are waiting for Honeywell and Siemens on the additive manufacturing side, and we are working with Solar Turbines on the combustion side. Again, if you want to write my motorbike, I'm glad to answer any questions. My motorbike is equipped with a very nice turbojet. It can only run at 180 miles per hour. I'm open to questions.
I'll take you up on that, Srinath. I'll write it.
All right.
If anybody has any questions, I think unmute or you can put them in the chat box or raise your hand.
And I can guarantee that when you're writing that, you are not going to feel your face. Any questions?
Yeah, just for curiosity. You look into the future of your field. You focus on the additive manufacturing.
Can you get closer to the mic, Fugu? I can't hear you.
Okay, let me see. I guess that you focus on the future by using additive manufacturing.
Right, that's right.
Did you also want to look at control part if you kind of enhance this performance in a way?
Right. So the idea is there are the two challenges. One is right now what people are doing is taking the same old design and printing it with additive manufacturing, and because that is the control design, right?
Yeah.
So they compare it, but there is no advantage to additive manufacturing because we are very good at relatively cheap, except for the casting does not use extra material, right? So casting is still not really subtractive manufacturing. It's not additive manufacturing. It's not subtractive manufacturing. Mm-hmm. So casting has been so popular in the companies that to replace casting, you need to come up with a very different option. That means you have to make designs that cannot be made with casting. That's the only way the world is going to change towards additive manufacturing. But right now, they are very good at casting. They can make anything with casting that they can make at relatively cheap. Mm-hmm. So additive can only be a game changer. It cannot replace what casting is doing.
Right, but you look into the 3D geometry, right. Theoretically, numerical algorithm can handle that, right? You can predict based on the additive manufacturing part.
Yes.
So somehow numerical can guide you.
Right. We do use numerical. We use numerical optimization before we actually make parts.
Right.
So the other interesting thing is when you make these parts, the question is when you put them in an engine, the FAA wants absolute certainty that this will survive the environment just like traditional parts because they have 40 years of history, right? So that's another challenge for additive manufacturing is to show the durability of the parts over the period of time because the grain structure is very different between a casted, cast cool or whatever the processes that they use versus additive manufacturing. They don't want any creep fatigue situations to occur, which will cause the part to crumble or collapse. And so that is where the challenge is the mechanical testing, thermomechanical testing of these parts is where the challenge is to make sure that they are as good as these cast parts.
That's right. Yeah.
Who else has a question? We got time for a couple more, I think here, one more at least.
Yeah, this is Mohammed. Enjoyed the talk very much, Srinath. In the beginning, you talked about material choices and temperatures and how close the temperatures are to the melting temperature.
Right.
But when you're getting into additive manufacturing, material choice is again a problem.
That's
Are they still focused on Inconel super alloys, or do you think, because a big thing with the materials is the thermal barrier coatings.
Right.
Are they able to incorporate any of these TPCs during AM?
No. So what they do is they are focusing is to make the blade, metal blade, just instead of casting, make it an additive, and then do the coating again. Then do the coating again. So they're not planning to do additive manufacturing of the coating.
Yeah.
So the coating will be done as traditionally as before.
Yeah.
But the only difference is that the metal part of the blade would be made with additive instead of casting.
I see.
So
and what's your feeling on? There's always a controversy with high temperatures. There's always that engineering solution of heat pipes.
right.
What's your feeling on using heat pipes as cooling instead of the films?
So you would need to use liquid metals like sodium and potassium.
Exactly.
So that is where the problem with the liquid heat pipe cooling is that you have to have molten metals but the problem is the corrosiveness of sodium and potassium has been, funny thing, Mohammed, you asked that great question because heat pipes came in the 80s, especially with the space program. A lot of people started doing heat pipes, and one of the very well-known the person who just stepped down as Georgia Tech president, Bud Peterson, actually, he did a lot of this heat pipe cooling. He and I actually had a conversation many, many years ago about doing heat pipe cooling for turbine blades. And we came up with the idea of doing sodium and potassium. And we talked about it. And when we went and I talked to the companies, they said, you know what, we actually thought about it already. And we tried some test blades. And unfortunately, the problem is that when we are non-operational, it takes some time for the sodium and potassium get up to the temperature and melt. As a huge energy required to convert from solid to liquid. By the time the part could fail, especially takeoff. So there are some issues with that. I mean, it's not like it's not been explored, but it's something that it's on the back of the mind of a lot of people. As I mentioned here in this plot here, right here, it says with heat pipe cooling, as you can see that. So there is still that idea that we can do this. But it has to be with sodium and potassium. It can be done. It is not something that it's been ruled out, but there are challenges. Like any problem, there are challenges with that. But it's a great question because heat pipes are very, very effective in cooling.
Okay, yeah. The corrosion effects are tremendous.
Yeah, that's exactly why they gave up on that.
Yeah. Okay, great.
Okay, I think we're 6 minutes over, so we'll wrap it up there. Thank you, Srinath. Excellent talk. I enjoyed learning more about what you're up to. And thank you to everyone that attended the seminars throughout the semester. We'll pick it up again next semester and hopefully fill in a little bit with some external speakers as well.
You can stop the recording, otherwise it'll, you have to wait till the last, I think. You have to be the last one to log out.
Yeah. I think, let's see, stop.